Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started.
You're out in a field, drone's ready to go, sky looks, pretty clear, maybe a few little clouds floating around. But are you really seeing the whole picture up there? Mm-hmm. Do you actually know what those clouds mean, or if they're about to throw a wrench in your flight plan? Today, we're doing a deep dive just for you, really focused on getting you that meteorological savvy you need for RPAS operations. We're going to unpack all your source material, looking at everything from the strict legal stuff to the pretty cool science behind why clouds even form, and we'll distill it all down into practical tips you can actually use. Our mission, to help you read the sky like someone who's been doing it for years, making smarter, safer choices up there. Because let's face it, knowing the legal distances is one thing, but actually estimating them, without instruments out in the real world, that's where the real skill comes in.
Yeah, and what's really fascinating here is seeing how all that historical knowledge from traditional aviation has been sort of adapted for drones. It puts a big emphasis on your visual judgment, your situational awareness, rather than just relying on complex instruments. And that's becoming even more critical with those 2025 amendments coming up. So this deep dive should really help bridge that gap for you.
Okay, so let's start with the basics, the absolute must-knows. When you're flying VLOS, visual line of sight, what are those fundamental legal separation rules for clouds? And thinking about drones specifically, what's maybe the trickiest part of actually meeting those rules for today's RPAS pilots?
Right. The core rules are pretty simple on paper. You absolutely must stay 500 feet below any cloud and 2,000 feet horizontally away from any cloud. These aren't suggestions, they're hard limits. And you'll often see them pop up indirectly in scenario questions for certification. Historically, early manned flight was almost all VFR, visual flight rules. Knowing clouds wasn't just academic, it was survival. After some really bad weather-related crashes back in the 30s, 40s, 50s, that's when formal weather theory, cloud types, precipitation, all that became a core part of pilot training.
Ah, okay. So it has deep roots.
Exactly. And that history is important because Transport Canada basically took those established principles when they brought in Part 9X of the cars for drones back in 2019. They adapted the 500 feet below 2,000 feet horizontal rules specifically for RPAS. Now, as for the trickiest part, I'd say it's often that horizontal 2,000 feet.
Yeah, I can see that.
Trying to judge that distance sideways with no ground references in an open sky, it's surprisingly tough. It really takes constant mental checking and recalibration. And there's a really crucial update coming in 2025. The amendment, SOR 2025-70, it adds a new requirement. You now have to document your weather risk mitigation if there's any precipitation forecast during your mission. It also gives clearer guidance separating VLOS and BVLOS hops. So yeah, starting in 2025, weather checks aren't just like a quick look anymore. It's got to be part of your formal pre-flight paperwork.
That makes total sense.
Yeah.
Documenting the risk. Okay.
Yeah.
So knowing the numbers is step one, but that horizontal piece, yeah, definitely a challenge.
Okay.
So how do you figure this out? You're standing there, drone ready. How do you estimate, say, the cloud base without pulling out complex gear?
Well, there's a surprisingly simple formula you can use, actually. If you have the local temperature and the dew point in Celsius, you can often get these from a METAR or even a basic handheld weather device. You can estimate the cloud base height in hundreds of feet AGL, above ground level. The formula is just temperature minus dew point, then divide that number by 2.5.
Okay.
So let's say the temperature is 20 degrees Celsius and the dew point is 15 degrees Celsius. The difference, the spread, is 5 degrees.
Right.
Divide 5 by 2.5, you get 2. That means your cloud base is roughly 2 times 100. Oh, wait, sorry. The formula actually gives it directly in hundreds of feet when divided by 2.5 from Celsius. Let me rephrase. Temp minus dew point in Celsius divided by 2.5, then multiply by 1,000 to get feet AGL. No, that's not quite it either. Let's reset that. The standard approximation is temp degrees, dew point degrees. 2.5 gives the base in thousands of feet AGL. Or if you use Fahrenheit, it's temp degree F, dew point degree is a 4.41 thousand. Let's stick to Celsius for simplicity here. So 20 degrees C minus 15 degrees C is 5 degrees C. Divided 5 by 2.5, you get 2. That means the approximate cloud base is 2,000 feet AGL. There we go.
Okay, got it. So temp minus dew in C divided by 2.5 gives you thousands of feet. 20 minus 15 is 5. 5 divided by 2.5 is 2. So 2,000 feet AGL. Makes sense.
Precisely. And beyond the math, there's a visual trick to the arm's length method.
Ah, the practical stuff.
Yeah. Hold your arm straight out, thumb up. Your thumb's width covers about 2 degrees of your vision. If you can fit your whole thumb's width vertically between your drone and the bottom of the cloud, you're likely looking at about 500 feet of separation, maybe more.
A literal rule of thumb.
Yeah.
Okay, thumbs up for 500 up. I can remember that.
Exactly. And for the horizontal distance, it's a bit more abstract. But try visualizing something familiar, like maybe a standard 2-story house seen at arm's length represents about 500 feet horizontally.
Okay.
So for 2,000 feet, you need to imagine about 4 of those house lengths stretching out sideways.
4 house hops for horizontal stop. These little mnemonics are actually really helpful. It makes it less, abstract.
Yeah, with a bit of practice, you start to get a feel for those angular sizes and what they mean in terms of distance. It also helps a lot to know your basic cloud types and where they usually hang out. Stratus clouds. Those are the flat, gray, featureless sheets. They often mean low ceilings, maybe 500 to 2,000 feet AGL. Bad news usually.
The blanket clouds.
Right. Then you have cumulus, the puffy cotton ball ones. They build upwards. Their bases are usually higher, maybe 2,000 to 6,000 feet AGL.
Fluffy clouds.
Then you get higher ones like altostratus, mid-level sheets, and cirrus, those really high, thin, wispy ice clouds way up, like 20,000 feet plus. Usually not a direct legal issue for most drone flights.
The feathers.
But the big one to watch out for, the major red flag for any pilot, is the cumulonimbus. CB.
The boom cloud.
That's the one. Massive thunderstorm clouds, huge vertical growth. Bases might start around 3,000 to 6,000 feet, but they go way up. You see anything that looks like a giant cauliflower growing vertically, even if it seems far off, avoid it. Assume the base is lower than it looks and the danger is significant. Stay well clear.
Got it. So puff, blanket, feather, boom, cumulostratus, cirrus, cumulonimbus. That's actually a pretty useful shorthand.
It works. And don't forget your drone's own tools. Your telemetry gives you altitude AGL, which is useful. But be careful with the FPV view, the camera feed. It can sometimes make things look further away than they are, compressing the distance visually.
Good point about FPV distortion.
And finally, always cross-reference with proper weather tools. Use NAV drone, check MEDARs, TAFs if they're available for your area. Those MEDAR codes are vital. Like BKN030 means broken clouds at 3,000 feet AGL. OBC020 means overcast at 2,000 feet AGL. And NAV drone often shows a forecast ceiling too, which brings up a really important point. What do you do when the forecast says one thing, but the sky right in front of you looks totally different?
Yeah, that's critical. Okay, so we have the rules. We have some estimation tricks. What's the science behind it all? Why do clouds even form? And why should a drone pilot care about stuff like adiabatic lapse rates? Seems pretty academic.
Well, it seems academic, but it directly impacts your flight. Clouds form when air gets saturated with water. You need 3 things. Water vapor, obviously. Cooling, because as air rises, it expands and cools, and colder air can't hold as much moisture. And condensation nuclei?
Condensation nuclei.
Like dust. Exactly. Tiny particles, dust, salt from the ocean, pollen, pollution. They give the water vapor something to condense onto. When the air cools down to its dew point temperature, boom, the vapor turns into tiny liquid droplets or ice crystals, and you see a cloud. Now, that adiabatic lapse rate, it's not just jargon, it's like an early warning system. Here's the key insight for you. Air cools predictably as it rises. Dry air cools faster, about 3 degrees Celsius for every 1,000 feet it goes up. That's the dry adiabatic lapse rate, DALR.
Okay.
But moist air cools slower, maybe 1.5 to 2 degrees Celsius per 1,000 feet. That's the moist adiabatic lapse rate, MALR. Why slower? Because when water vapor condenses into cloud droplets, it actually releases a bit of heat, latent heat.
Like sweating cools you down, condensation warms the air slightly.
Kind of, yeah. And that slower cooling means clouds can form much lower down on humid days than you might expect. A seemingly okay morning can turn into a low ceiling situation really fast once the ground heats up and air starts rising. It's why humidity matters so much.
Okay, so it helps you anticipate how fast that ceiling might drop.
Oh, got it.
And the way the air gets lifted also determines the cloud type and therefore the risk.
Precisely. Different kinds of lift create different clouds and different hazards. You've got convective lift, that's the sun heating the ground, causing warm air parcels to rise. That makes your puffy cumulus clouds, and potentially those dangerous cumulonimbus, CBs. Think midday thermals.
Right.
Then there's orographic lift. Air forced up and over terrain like hills or mountains. That often creates stratus clouds banked up on the windy side, or sometimes those cool, smooth, lenticular clouds near mountains. But that terrain link often means turbulence.
Lenticular, those are the lens-shaped ones.
Yeah. Beautiful, but often signal rough air. Then you have frontal lift warm air riding up over colder air along a weather front. That typically gives you widespread sheets of stratus or nimbostratus, often bringing steady precipitation. And finally, mechanical lift, just wind blowing over obstacles like buildings or even trees, creating turbulence and sometimes small, scuddy clouds. Knowing the likely lift mechanism helps you predict the cloud type and the associated risk.
Makes sense. Lift equals cloud type equals risk level.
Exactly. And for precipitation, there are basically two ways it forms. In warmer clouds, it's collision coalescence. Tiny droplets bump into each other, merge, get bigger and heavier, and fall. But in colder clouds, common here in Canada, it's usually the Bergeron-Finn-Dyson process. Tiny ice crystals grow by attracting water vapor from surrounding supercooled liquid droplets, which haven't frozen yet, even though it's below zero. These ice crystals get big enough to fall as snow or melt into rain on the way down.
Supercooled droplets. That sounds like a problem.
It is a huge problem. Supercooled large droplets, or SLD, are water drops that stay liquid way below freezing, sometimes down to -40. When your drone flies through them, they freeze instantly on contact. This is aircraft icing, and it can build up incredibly fast, ruining aerodynamics, adding weight, potentially causing a crash.
So it's not just about avoiding visible rain or snow. It's this invisible icing threat, even in just cloud. You need to know the temperature profile.
You absolutely do. It's a critical hidden danger. And speaking of water in clouds, here's a fun fact. An average cumulus cloud, one of those puffy ones, it can hold over 500,000 kilograms of water.
Get out. That's insane. Like more than a jumbo jet.
Way more. More than a blue whale even. But it floats because the droplets are incredibly tiny and spread out over a vast volume of air. Still mind-blowing amount of water up there.
Wow. Okay, so bringing this all down to earth, or rather, keeping the drone safely in the air. This is where the rubber meets the sky, right? How do all these insights actually play out when you're flying? What should you be looking for, and what's the immediate reaction when things start looking iffy?
Right. This is about applying the knowledge, making quick, conservative calls. A good way to remember the key warning signs is the 4 clues to trouble. I call it CDCV. Clouds don't care, verify.
Okay, CDCV. What are they?
Is the ceiling visibly dropping? Are the clouds getting lower? Is the dew point spread getting tight? Less than 2 degrees Celsius difference between temp and dew point often signals fog or low cloud is imminent or present. Are cumulus clouds growing vertically, looking like cauliflower? That's a sign of increasing instability, potential CDs. And are you seeing virga, those streaks below cloud?
Virga, right, you mentioned that. It looks like rain that doesn't reach the ground. Sounds harmless, but you said it's not.
Definitely not harmless. That evaporating rain cools the air beneath the clouds significantly. Cool air is denser, heavier, so it sinks fast. Virga is often a sign of strong downdrafts, gusty surface winds, sometimes even dangerous microbursts right below it.
Ah, okay, so it's pulling air down hard.
Exactly. If you see virga, expect turbulence underneath. Don't fly under it thinking it's dry.
Virga is Vapor's version of a sucker punch. Got it.
Oh.
Okay, let's try a scenario. Call it Operation Cloud Deck. You're planning a VLOS flight, maybe inspecting power lines, the METAR says. Broken clouds at 3,000 feet AGL. Overcast layer higher up at 7,000. Temperature is 14 Celsius. Dew point is 12 Celsius. Your plan is to fly at 400 feet AGL. What's the thinking process here? Go or no go?
Okay, let's walk through it for you. First, that temp dew point spread. 14 minus 12 is only 2 degrees Celsius.
Tight spread. That's one of the D clues from CDCV.
It is. That alone is a caution flag. Now let's estimate the cloud base using the formula 1412, 2.5 equals 2.5 is 0.8. That translates to about 800 feet AGL for the base of that broken layer.
Okay, 800 feet AGL cloud base.
Right. Now, your planned flight altitude is 400 feet AGL. So the vertical separation between your drone and the cloud base would be 800 minus 400, which is only 400 feet.
And the rule is 500 feet below.
Exactly. You need 500 feet minimum vertical clearance below clouds for VLOS. With only 400 feet, you'd be violating the rules.
So the call is,
It's a clear no-go under these conditions. You either wait for the clouds to lift significantly, or you adjust your mission profile to stay much lower, ensuring that 500-foot buffer. Always trust your calculation and what you see over maybe an old forecast.
Makes perfect sense. Safety first, rules first. Okay, what about risks that pop up during the flight? What do you watch for and how do you react?
Yeah, conditions change. You need to be constantly scanning. If you notice that ceiling starting to drop, especially if you knew the dew point spread was tight, get ready to descend or return to home immediately. If you're near mountains and you see those smooth, lens-shaped lenticular clouds forming...
The pretty but dangerous ones.
Exactly. Recognize them instantly as a sign of potentially severe mountain wave turbulence, maybe even rotor clouds underneath. Don't try to fly through it or even near it. Cancel the mission in that area or relocate far away.
That Chinook Arch we get in Alberta looks calm, but it's formed by that mountain wave, right?
Yeah.
So, danger sign.
Absolutely. Beautiful arch, potentially very rough air. Also, be really cautious about embedded CBs, thunderstorms hidden inside layers of other clouds. You might not see the classic towering shape. Rely on MEDARs mentioning CBs, check weather radar if possible, and trust reports from your visual observer if they see anything suspicious. And one more. Watch out for that deceptively calm, clear morning, especially after a cool night. It could be a radiation inversion.
Meaning
Cold, still air trapped near the surface, but potentially much stronger winds just a few hundred feet up. You'll launch in calm air, climb a bit, and suddenly hit strong wind shear. It can mess with your drone's stability and even GPS accuracy.
Wow, okay. Lots to watch for. Is there a simple framework to keep all this in mind?
Yeah, a good mental model is look, listen, layer. First, look. Actively observe the clouds' shape, movement, how they're layered, signs of growth or dissipation. Second, listen. Pay attention to weather cues as the wind picking up or shifting. Hear any thunder, what's your visual observer reporting? And third, layer. Understand the atmosphere. Think about stability, that critical dew point spread, potential inversions, different wind speeds at different altitudes.
Look, listen, layer. I like that. It ties everything together. It feels like the best pilots aren't just reacting. They're constantly anticipating based on these layers of information.
That's exactly it. They make conservative decisions, often quite quickly, based on subtle visual cues backed up by the science, and they always have an exit strategy, a plan B.
Okay, we've covered a lot, the rules, the estimation tricks, the science, the real-world reactions, but what takes it to the next level? What does, true mastery of sky reading look like for an RPS pilot, and what's on the horizon future-wise?
Well, true mastery goes a bit deeper into things like cloud microphysics, understanding how the actual size of the water droplets or ice crystals, their density, and whether they're liquid or ice, the cloud phase, how all that impacts your drone's sensors.
You mean like how well the camera sees or thermal imaging works?
Exactly. Dense clouds with large droplets can mess with optical sensors, reducing visibility significantly. Ice crystals scatter light differently than liquid drops. It can affect thermal contrast, and dense moisture can even attenuate your GNSS signals, making GPS less reliable.
So if your own glasses would fog up, you should assume your drone's camera might be having issues too, maybe even internal connections. That's a good way to think about it.
It is. And beyond the tech, mastery is also about reading the sky with the kind of intuition an old-school sailor might have had. Looking for those subtle visual cues beyond just the basic cloud types, like seeing a cloud with a very flat, dark base, but a sharply defined bright white rising tower above it. That screams strong updraft, potential CB development. A really sharp, clear edge to an advancing cloud bank often signals an approaching cold front, meaning rapid weather changes are coming.
And you mentioned halos around the sun or moon earlier.
Yeah, those are caused by high-level cirrostratus clouds made of ice crystals. They often show up 24 to 36 hours ahead of an approaching warm front, which usually brings deteriorating weather and precipitation. It's an early heads up.
It's amazing how many clues are up there. I even heard you can sometimes smell rain coming, that earthy smell. Tetracore.
You can. It's about using all your senses, really. Another level is understanding the typical life cycle of cloud formation, growth, maturity, dissipation, and knowing the hazards associated with each stage. Experts don't just see a cloud, they see where it's likely headed. And knowing diurnal patterns, how weather tends to change through the day. Morning fog or low stratus often burns off. Midday heating brings thermals and cumulus development. Late afternoon, especially on unstable days, is prime time for thunderstorms to pop up. Using the time of day itself as part of your forecast.
Okay, so it's about integrating everything.
Absolutely. Deep understanding needs to be combined with constantly checking your tools. NEV drone, GFAs, graphical area forecasts, satellite imagery, and really being fluent in reading those METARs and TAFs. No single piece gives the full picture. You layer the information. Looking ahead, the future is likely more tech integration. Think AI-powered weather analysis on board the drone itself, sensors that can estimate cloud base height or density in real time, maybe even dynamic no-fly zones that pop up automatically on your controller based on live radar showing heavy precipitation or severe cloud growth nearby.
Wow, real-time automated hazard avoidance.
Yeah, and we also have to factor in climate change. It's making weather patterns more extreme and less predictable in some ways, so that need for robust real-time meteorological awareness is only going to increase. We might even see flight software using the drone's own camera for visual recognition, identifying dangerous cloud formations automatically. And just one last mind-bending fact to leave you with. The tallest clouds on Earth, those monster CBs, can tower higher than Mount Everest. We're talking 60,000 feet or more, way up into the stratosphere.
60,000 feet. That's incredible.
Yeah, high enough they can actually punch through the tropopause. Inside those giants, you've got extreme turbulence, hail, lightning. Definitely no place for a drone or much else.
Wow. Okay, so we've definitely journeyed through the clouds today, covering everything from the ground rules to, well, the stratosphere. It's been incredibly insightful.
Yeah, hopefully this deep dive really drives home that mastering the sky isn't just about ticking boxes or knowing the rules by heart. It's about blending that cloud science, the visual interpretation, the tech tools, and honestly, good seasoned judgment to make sure every single flight is as safe as it can possibly be.
It really feels like the sky is constantly communicating with us, doesn't it? If we just learn the language, learn how to listen and look properly. So here's something for you to think about. The next time you step outside, what subtle change in the clouds might you notice that you wouldn't have before? And what might that tiny shift be telling you about the air all around you?
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.